Hey guys, sorry for not uploading, I slept in a little bit. Anyway, in this video I'll be doing a simple combinatorics proof, but in a more complicated manner than you would usually see it, and I'll be using group theory, as well as what are known as unsigned Stirling numbers of the first kind. So the basic question I'll be asking today is, how many unordered strings of length k can I create by drawing from an alphabet of n symbols with replacement? So that probably sounded like a bunch of gibberish, but if I give an example, you'll probably understand it just fine. So let's go ahead and say our alphabet is A, B, C, D, E, F, G. So these are just all of the symbols that we'll be creating our strings with. And so this is an alphabet with a number of elements equal to 7. Now, from this alphabet, I'll create a string that's, say, 5 symbols long. So this would be an example where k is 5. So I just draw from this alphabet to create any arbitrary string. So let me go ahead and say C, F, D, G, C. And the reason I'm able to have that C twice is because I'm drawing with replacement. So because I have the ability to replace what I'm drawing from, it just means I'm able to have it twice. But there's also another requirement, which is that these strings are unordered. And all that means is that it doesn't matter the order you place these strings into. So for instance, I could rearrange this string so that it looked like D, C, F, C, G, because C appears twice on the top and the bottom, and D, F, and G appear once. These are the same strings, because these strings aren't actually ordered. The order that these symbols appear in doesn't matter. How many of those strings can I create? Well, that's a bit more of a complicated question than you might realize, because, for instance, I could do A. This symbol doesn't have any reorderings. There's no way I could rearrange those symbols because they're all the same. But something like A, B, A, well, I can move this B around. Right? I could have AA, and that'd be the same string. And there's a bunch of ways to rearrange that, but depending on the symbols you have in the string, there's a different number of rearrangements you can have of that string that is an equivalent string. So how do I actually count the number of these unordered strings? That becomes a little bit difficult. Now, when I heard this problem, what it immediately reminded me of are things called group actions, and specifically permutations. So I'm going to explain what a permutation is right now, in case you don't already know. So a permutation, I'll probably call it sigma. And all a permutation is that you have some set of symbols. So I'll go ahead and do the numbers. 1, 2, 3, 4, 5. Those are my symbols. And I just rearrange them in any way that I see fit. So I could do, say, 2, 3, 1, and 5, 4. So in this original, we have 1, 2, 3, 4, 5, and I just rearrange them so that 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 5, 5 goes to 4. And so I get a new string based off of that original string of 5 characters. And note that you aren't drawing with replacement, and those are ordered, right? So the order matters, and you can't have a repeat symbol. So you might immediately recognize that the number of permutations will be related to the factorial. Let's go ahead and see why. So if we're generating an arbitrary permutation, this 1 could go to an arbitrary symbol at the beginning, right? It could be any of the 5 original symbols it can go to. So we have a choice of 5 different symbols there. But this 2 can't go to the same symbol as the 1 because we're just reordering the original 5 symbols. So we actually only have 4 symbols available for 2. And then this 3 can't go to the same one as 2 or 1. And so we only have 3 symbols available, 2 symbols available for 4, 1 symbol available for 5. You multiply all those together, and you get 5 factorial. But in general, it'll just be k factorial. So if I have k symbols up here at the top, there are k factorial many ways to rearrange it using a permutation. Now, there's actually a better way to write out this permutation that will be more useful for our purposes today, which is cycle notation. So the way cycle notation is you just follow where one of the symbols go, and then eventually loop back, and you just write it out in a way that expresses that. What do I mean by this? Well, let's go ahead and follow where 1 goes. So 1 originally goes to 2, right? So the symbol 1 at the top goes to 2. So I'll write 1, 2. And then 2 goes to 3. So 2, 3. So 1 goes to 2, goes to 3, and then 3 goes back to 1. So the way I express that is just by putting parentheses around it. So this means that 1 goes to 2, goes to 3, loops back around, because we have the parentheses, 3 goes to 1. And so that's just a compact way of representing the same idea that I've represented here. Then, let's go ahead and see what happens if you follow 4, because we don't know where 4 goes just based on this cycle. So 4 goes to 5, so 4, 5, and then 5 goes back to 4, and so it loops back around. And so any permutation you can represent using this cycle notation. And so this sigma that we have here, represented in this matrix form, is also the same as this cycle form. And this cycle form is going to be really useful for the future. If you're still a little confused about these cycles, I'll link a Mathologer video in the iCard somewhere, which talks about cycles and Futurama. Now we can talk about the set of every permutation on k symbols. And I'll represent the set of all of those symbols by S sub k. Now S sub k is actually what's known as a group. And all a group is just some set, in this case the permutations, under some operation between those. In this case the operation is just composition. I do one permutation, then I do the next permutation on the set of symbols. And you also need to have it that this operation can be undone, like how division undoes multiplication. So I'll link a 3 blue 1 brown video or maybe a lecture series about groups in the iCard. Okay, now that we understand these permutations, what does this have to do with our original question about these strings? Well, the thing is that I can have these permutations act on the strings. What does that mean? Well, I can do sigma applied to one of our strings. Let's go ahead and do the original string I had. So C, F, D, G, C. So how do I apply this permutation to this string? Well, I just view these numbers as the place the symbol is, alright? So in the case of sigma, the symbol that's in place 1, so C in this case, goes to place 2 in the output. So C goes to place 2. And then the symbol that's in place 2, which is F, goes to place 3. So F moves to place 3 in the output. And then the symbol that's in place 3 moves to place 1. So D moves to the start. All right? And then 4, which is G here, 4 moves to 5, and 5 moves to 4. So C, G. And you can see that this is the same rearrangement we had originally. So we had CF, DG, C, and we rearranged it to DCF, CG. And so this rearrangement, which was supposed to show 2 equivalent strings, is the same thing as a permutation applied to that string. So all of the rearrangements of this string is actually just a permutation applied to that string. Why is that important? Well, it's because we can talk about what are known as orbits. And so the way I'll represent it as an orbit is just write SK, which represents all of the permutations, right? So in this case, it'll be S5, and I write S5 and then the string I'm applying it to. So an orbit is just the collection of all of the strings that you can get from rearranging one string. So for example, here I could do the identity permutation, right? So that's just no rearrangement. But I could also rearrange it in this way, by this sigma. So I could get the string DCFCG. All right, I could rearrange it in any way I want, as long as it's the same symbols and appearing the same number of times. This orbit, all of the different permutations applied to a single string, is just all of the ways you can rearrange that string. And so this orbit represents all of the equivalent strings if they're unordered. So all of these strings are equivalent because they're just rearrangements of the same symbols. So what we're actually counting, when we're counting the unordered strings, is just the number of orbits. And the number of orbits of all the strings are related to a concept known as fixed points. So let's go ahead and look at our example of this sigma. What's an example of a fixed point for this sigma? You might be able to guess. We could do, say, FFFAA. This is a fixed point by this sigma. How so? Well, let's go ahead and apply sigma to it. The symbol that's in the first spot goes to the second spot. Symbol in the second spot goes to the third spot. Symbol in the third spot goes back to the first spot. you can see it stayed the same. Same thing with this. Symbol in the 4th spot goes to the 5th spot, 5th spot goes to the 4th spot. Those were both A. I applied the sigma to a string, but it didn't change anything. This rearrangement didn't do anything to this example of a string. And so this string is known as a fixed point of sigma. So how are these orbits and these fixed points related? Well, it's by something called Burnside's lemma. Burnside's lemma basically says that the number of orbits, which I'll represent by bracket x divided by sk, where k is the length of this string that we're choosing, and x is just the set of all of these strings, right? So I'm doing this set x, all of our strings, under orbits by the permutations. So the number of orbits is equal to 1 over the number of permutations times the sum for all permutations, their number of fixed points. So this represents the set of fixed points, and then these this absolute value sign means the number of. So the number of fixed points, add them all up for all permutations, divide by the order of the group, or the number of permutations. Alright, so another way to think of this is the number of orbits is the average number of fixed points for a permutation. Alright, how is this useful for our problem? Well, it's actually easily calculable. Let me explain. We already know the number of permutations. I talked about it. It's k factorial. Those are the number of ways you can rearrange k symbols. Now, this sum is a little bit harder to immediately realize, but let's go ahead and look at our example of a permutation. Right, 1, 2, 3, 4, 5. Given this example, how many fixed points are there of it? Well, let me give an example of a fixed point of this permutation. I already did, but I'll give you another one. AAA, BB, right? Why does this work? Well, because 1 goes to 2, so A goes on to where A used to be. 2 goes to 3, so A goes to where A used to be. 3 goes back to 1, A goes back to 1. Alright, so the reason this works is because every symbol in this cycle was the same. And because all of these symbols are the same, they end up not changing under this cycle. Same thing with this one. Because all the symbols in this cycle are the same, they end up just mapping onto each other and remaining the same string in the end. Okay, let's go ahead and do a bit more of a complicated example, say on 7 different symbols. Let's go ahead and say we have a cycle of 1 and 2, and we have a cycle of 3 and 7, and we have a cycle of 4, 5, and 6. So all we need to be able to generate a fixed point of this is that all of the symbols in all of the spots in these cycles are equal to each other. Alright, so the symbol in the first spot has to be equal to the symbol in the second spot. Why? Because they swap places. If we have a fixed point, you need it so that they're the same symbol when they swap places. Same thing with 3 and 7. 3 has to be the same symbol as 7 because they swap places. You need to have them be the same if you want a fixed point. Same thing with this. All of these have to be equal to each other because they swap places with each other. So you can see that this is a fixed point. But the basic idea is that for each of these cycles, you can choose any point as long as all of them in the cycle are the same symbol. So there's n choices for a symbol for this cycle. I pick one of the symbols and they all have to be the same. Same thing with this. There are n different symbols I can choose from because we're doing this with replacement. And so there are n different ways to choose this cycle. They all have to be the same. So you pick one of the symbols and all of them are the same for that cycle. Same thing here. So the total number of fixed points for this permutation is just multiplying all those together, n cubed. Same thing with this. There's n symbols for this cycle that you can choose, and n symbols for this cycle you can choose. And so you get n squared. So you might notice that in general, it's just n to the number of cycles, right? Each of those cycles, you can pick any of the n symbols that we have in our alphabet, as long as within each cycle, it's all the same symbol. So it's n times itself by the number of cycles. It's n to the number of cycles. That's the number of fixed points for an arbitrary permutation. What this tells us is that the number of fixed points for a given permutation only depends on the number of cycles, right? So let's go ahead and say we have sigma 1, sigma 2, all the way up until, say, sigma r. And let's go ahead and say they all have the same number of cycles. Let's say they all have I cycles. That means that there's n to the I fixed points for sigma 1 and n to the I fixed points for sigma 2 all the way up until n to the I fixed points for sigma r. So if I'm adding all of these up, all I get is r times n to the I. And so when I'm doing this sum, which is the sum of the number of fixed points for every permutation, all I have to do is add up. Let's go ahead and say I is the number of cycles. So I equals 1 to k, right? So I could have a single cycle, or I could have k different cycles. Then for each of these number of cycles, there are going to be n to the I number of fixed points for each permutation, but there's going to be some number of permutations that have I cycles. And we're going to say that that number of permutations is ki in brackets like this. This ki in brackets, this is the number of permutations on k symbols that have I cycles. This is called the unsigned Stirling number of the first kind. I'll just call it k Stirling I. The sum of the number of fixed points for every permutation is just equal to the sum of the number of permutations that have I cycles times n to the I. This polynomial that we get here is actually easy to compute. It has an easy form. Let's go ahead and see how. This is the form we ended up with, but it looks just as daunting as the original form. So how on earth could we possibly evaluate this? Well, it's actually really easy if you just know a couple properties of these Stirling numbers. Specifically, there is a form of this ki, this k Stirling I, where I represent it in terms of the permutations on k-1 symbols. And the way I do this is by splitting up into two different classes. The first class is where k goes to itself. So let me go ahead and draw out an arbitrary permutation, and I'm representing for each of the symbols just dots so that I don't have to get specific with anything. And it looks like this, right? So we have a bunch of, whatever permutation here, and then we just have k going to itself, which is a 1 cycle. So there's a total of I different cycles here that compose this whole permutation. But you might notice that because it's just a single k off to the side, a 1 cycle, the number of permutations that look like this is the same number of permutations that look like just this section, right? With I-1 cycles and k-1 symbols. Because all I do is generate one of these permutations with I-1 cycles and k-1 symbols, and then I just add this on the end. And so the number of this whole k permutation is the same number as this k-1 permutation. So this first class has k-1 Stirling I-1 different permutations in it, because there's k-1 symbols here, I-1 cycles, and then you just add on k. So that's our first class. What's our second class? Well, it's in the case where k doesn't go to itself. Alright, in this case, we can just represent it as a k-1 cycle again. Right, let's go ahead and say this is our k-1 cycle, so there's only k-1 symbols in here. And then we just add k somewhere into it, right? So I could choose to add k right there at the beginning, or right there in the middle, or right there at the end. Maybe at the beginning, middle, end, right? And so anywhere I add k in, that'll be a different permutation. And so if we're counting the number here, it'd just be the number of k-1 permutations that look like this. So that would be k-1 symbols we're doing the permutation on, and I cycles. But then we have a choice of where we add k in, and so we have to multiply it by something. Well, it's just the number of places where you can add k in. But I want you to notice something. If I add k in at the beginning here, it's the same as if I were to add k in at the end, because it loops back around, right? If k is at the beginning, it goes to this first dot. But if k is at the end, it still goes to that first dot. And so we've overcounted a little bit, and we just have to get rid of those. And you might notice there's 2 symbols in this cycle, 2 symbols in this cycle, and 2 places where you can place k. And so all it is just the number of symbols. That's the number of places where you can put k. You can put k in any of these places, but the total number of those places where you can place k in to make a new permutation on k symbols is just the number of symbols, which is k-1. You can generate any of these k-1 permutations with I cycles and there's going to be k minus 1 places where you could add kn to create a k permutation. These two classes compose of all of the permutations, and so the number of permutations on k symbols with I cycles is equal to the number of permutations with k minus 1 symbols with I minus 1 cycles plus k minus 1 times the number of permutations with k minus 1 symbols and I cycles. This is our property, this is our identity with the Stirling numbers that will make this easy to evaluate. To see how we can use this identity, let's go ahead and look at a few examples of that polynomial. Well, let's go ahead and do the example where k is equal to 1. So we only have one symbol we can move around. Alright, so this is going to be the sum from I equals 1 to 1 of ki times n to the I. So this is just the first Stirling number 1, 1, 1 Stirling 1 times n. What's 1 Stirling 1? How many permutations on one symbol can you make that has one cycle? Well, it's the permutation where 1 goes to itself. That's the only permutation. So you just get n. Alright, what about in the case where k is equal to 2? Well, in this case, we now have two different symbols we could rearrange. So we have 2, 1 times n plus 2, 2 times n squared. 2, 1, so how many permutations on two symbols can you make that has one cycle? Well, it's this one. It's always 1, right? It's just 1 goes to 2, 2 goes to 1. Alright, so that's 1, so we just get n there. But what about two symbols, two cycles? Well, there's only one way to do that too. It's where 1 goes to itself and 2 goes to itself. And so I just get n plus n squared. And now I'm going to write this out, maybe a little bit of a weird way, but it'll make sense as we go along. It's n times n plus 1. Alright, let's keep going. What about k equals 3? We have 3 different symbols. Let's go ahead and use our fact right here, which is ki is equal to k minus 1, I minus 1, etc., etc. So our polynomial is equal to 3, 1, n plus 3, 2, n squared plus 3 Stirling 3, n cubed. We can use our fact to evaluate each of these Stirling symbols. So 3, 1 is equal to what? Well, it's equal to, by that fact, it's equal to 2, 0. So 2, 0 is just 0, I'll tell you that. Plus, and then k minus 1 is 2 times 2, 1. And we know that 2, 1 is just 1. And so we just get 2 for this 3, 1 here. So we get a 2 there. Alright, what about this 3, 2? Well, we can do the same thing. It's 2, 1 plus 2 times 2, 2. Well, we know what both of those are. That's a 1, so that's a 2. And we know that 2, 1 is a 1. And so we get a 3 for this one. And then 3, 3, this one we actually don't have to use the formula for because it's just a number where all of them are 1 cycles. And there's only one way to do that. And so we get n cubed there. So first thing we can do is factor out an n, and then we get 2 plus 3n plus n squared. And that can be factored. You know, you can think about how you factor things. That can be factored into n plus 1 times n plus 2. And so you probably already see the pattern. We have n, then n times n plus 1, then n times n plus 1 times n plus 2. And so the general formula for k, is n times n plus 1 all the way up until n plus k minus 1. Right? Because this only goes up to n plus 2 for k equals 3. Alright, so how do I actually prove this general formula? Well, the way I'll do it is by induction. I'll assume that this general k is true, and then using that, I'll prove that k plus 1 is true. So let's go ahead and write out the statement for k plus 1. Alright, and the statement for k plus 1 is that n times n plus 1 all the way up until n plus k is equal to the sum from I equals 1 to k plus 1 of k plus 1 Stirling I times n to the I. So that's our statement, and given this statement for k, we have to prove this statement for k plus 1. Well, I'll go ahead and rewrite the statement for k, except all out explicitly, and it's n times n plus 1 all the way up until n plus k minus 1 is equal to the sum from I equals 1 to k of k Stirling I times n to the I. All right, what can I do with this formula to figure out this formula? Well, you might notice I can multiply both sides by n plus k. If I do that, what I have here on the side is n times n plus 1 all the way up until n plus k minus 1, and then times n plus k. And then on this side, I'll have n plus k times this sum. All right, what I'll do is distribute the n and the k in. So what I get, write it down here, is first distributing the n in, I get, n times all of these terms. Well, n times n to the I is n to the I plus 1. So I get k Stirling I times n to the I plus 1. Now what I'll do is instead of writing I plus 1 here, I'll reduce it down to an I. And instead of an I there, I'll write an I minus 1. And instead of 1 to k, I'll do 2 to k plus 1. All right, that's the same sum because all I did was plug in I minus 1 for I. Then I have to distribute the k in. And so if I just multiply all of these terms by k, I get k times k Stirling I times n to the I. Now I could do a little trick here, which is instead of saying from I equals 2 to k plus 1, it's the same as I equals 1 to k plus 1, because if I plug in I equals 1 here, I get a 0 for the number of cycles. And there are 0 permutations with 0 cycles, and so that's the same sum. And then I could go all the way up until k plus 1 here, because if I plug in k plus 1 for I, the number of permutations on k symbols that have k plus 1 cycles is 0. And so that ends up being the same sum as well. Now you can see I have these same bounds, and so I could just combine these two sums into the sum from I equals 1 to k plus 1 of, I have k Stirling I minus 1 plus k times k Stirling I, and both of those times n to the I. And so if I just factor out that n to the I get this form. You might notice this right here is our formula. So right there is the same thing as k plus 1 Stirling I by our formula. And so we end up getting at the end that this term right here, which was always on the left, is equal to the sum from I equals 1 to k plus 1 of k plus 1 Stirling I times n to the I. And so by induction, we have a general formula for this sum right here, which is n times n plus 1 all the way up until n plus k minus 1. And this is known as the rising factorial. And you might be able to tell why, because it's just a factorial function, but you're going up instead of down. And so if we just plug this in, we'll be able to get our answer. Now that you understand that this polynomial is just a rising factorial, let's go ahead and plug that in. So we have 1 over k factorial times, what's going to be n times n plus 1 all the way up until n plus k minus 1. So this can actually be rewritten in a way that might make you realize something right away. It can be rewritten as n plus k minus 1 times all the way down until n, right? You just decrease by 1 every time down to n. And we're dividing this by k factorial. But what we could do is continue multiplying down on the top. So we could multiply down by n minus 1 as long as we also multiply the bottom by n minus 1, because that cancels out. And so n minus 1 on the top and bottom, and then n minus 2 on the top and bottom, and then all the way down until 1 on the top and bottom. And you might immediately recognize that this right here is just n plus k minus 1 factorial. And this stuff on the bottom is just k factorial times, and that's n minus 1 factorial. You might notice something, which is that this looks like a choose function. And that's because it is. It is n plus k minus 1 choose k. And you can go ahead and look at the formula for choose. This works out just fine because this n minus 1 is the same thing as n plus k minus 1 minus k. The k's cancel, and you just get n minus 1 there. This is the final form we have. Isn't that spectacular? This proof is beautiful. it takes you through group theory, it takes you through Burnside's lemma, and then you get it into the form where you have the coefficients equaling the unsigned Stirling numbers of the first kind, and then you need to know that this polynomial is actually equal to the rising factorial, which is just such an interesting property of these unsigned Stirling numbers of the first kind, until eventually you get it into a form that's equivalent to the choose function. So I'm sure there are easier ways to prove this formula, but they're not nearly as cool as this one. Anyway, that's it.